Hello, I'm Brian Brain, and I'd like to welcome you to the Joy of Engineering series. I'll tell you what, I'm going to have them run the equations that we're going to be using today across the bottom of the screen while I show you what I've got set up over here. You'll see that I have my 18 by 36 whiteboard with a few dry erase markers for performing my calculations. I strongly encourage all of you at home to follow along as I figure out what this model is all about. And it's alright if you haven't got a dry erase board. Any old paper and pencil will do just fine. I've gone ahead and drawn out the free body diagram of the model we're going to be analyzing today, as well as a table of some values in order to save us a little bit of time. And a nice little real-life example of the structure here right next to me. Now at first glance, you might think that this funny little table is impossible. It appears as if the top portion is defying gravity by just being held up by these three strings. Our brains are used to seeing tables held up by table legs, and those legs are normally in compression. In this here table, the strings are still holding this table up, but they're actually in tension, not compression. So when you press down, the strings become tighter, height-wise. So over here at my whiteboard, excuse me, you can see my free body diagram of the side view of the table. From this view, we could see that we have three forces acting on our tabletop. The weight of the table, right there, acting at its center of mass, the tension in string 1 preventing the table from tipping over, and the tension in string 2 that is countering the other two forces. To simplify things a bit, we're assuming that the tension in string 1 is the combined tension in both strings on the front of the table. Now, since we know that the weight of the table, which we calculated just by weighing the components of the tabletop itself, we're left with two unknowns, which are each of these tensions here. Whoa, I accidentally erased that a little bit. To solve for these, the first thing we could do is take the sum of the moments about a certain point on this table. Now, I lost my black marker. There it is. So, I'm not sure about you, but my favorite part about starting out any statics problem is writing out the sigma. So, I like to start it out a little up here, do a little zig, zag, zig, zag, boom, done. That's our sigma. You could add a little funny little marks there and there if you want to. It's completely up to you. Oh boy, table just fell over a little bit. Hang tight. That should be good. All right. Oh boy, we're gonna do that some of the moments about T2, because that way, I mean, realistically, we could take the sum of the moments about any point on this table, but we're gonna do the sum of the moments about T2. Let's set that equal to 0. A little smiley face because we're feeling happy today. And the sum of the moments is going to be W Cm times its distance. Right here, we're going to call that distance L. And then we're going to do minus, because it's going clockwise, T1 times, we could go up here, figure all that out. I'll just tell you, it is 45 millimeters. Perfect, boom. Now if you're following along, you realize that another unknown just popped up, and that's our distance from the weight to T2. In order to solve for that, we'll jump on over to our table here that's already set up for us. Luckily, we'll only need the y bar coordinate of the center of mass, since the weight only has a vertical component. These yi values are obtained by understanding that the center of mass along the y-axis of each of these shapes here will be half of their length plus their distance from the origin, which I've marked over here. So half their length, because they're rectangle. So in this case, you could see it would be, so this is shape 1. We have 5 millimeters from the origin to this point, then half of 55 over 2 plus 5 millimeters gives us 32.5 millimeters. Repeat the same steps for these two parts up here. Since this one actually meets up with our origin, we could just call that 50. Now, we multiply that, the yi value, by the volume of each of these shapes. When we do that, we get millimeters to the fourth over here. We could see here that vi times yi over the sum of all of these. So we have the sum here divided by that. So that's going to be 1,310,625 millimeters to the fourth over 28500 millimeters cubed. That gives us 46.0 millimeters. So that tells us that our y bar up here equals to 46.0 millimeters. So then we could take that, figure out this L distance here, which is what we were looking for in the first place. All right, so now that we have this distance here, you could probably see it better from that angle, we can figure out what our distance L is. So L will just be, let's see here. So we are left with L equals 4 millimeters. Perfect. Again, so actually what we're trying to do is figure out the max weight. So ignore the 0.255. We'll just call that W. So T1 equals 4 over 45 W. So now we could apply that to T2, take the sum of the forces in the y direction. We get that T2, which is the only positive force acting, minus 4 over 45 W minus W, which, 45. You could just call that 45 over 45. That's 49 over 45, so we get T2 equals 49 over 45W. So now this tells us that T2 not only has to carry the load of the table and anything placed on it, but it also needs to be able to counter the downward force that T1 enacts on the top of the table. Since we know that the string at T2 is the governing member of this system, since it clearly supports more load, we can use the material properties of the string to figure out how many packs of gum this baby can hold up on it. From research, we could figure out this specific type of string, which is 16 ply, trust me, I counted it, has a maximum tensile strength of 40 pounds. We can convert that to newtons, knowing that there are about 4.48 newtons, so we get that the max strength of the string, STR, equals 178 newtons. Perfect. So we could come down here, figure out that so we got 178 newtons equals 49 over 45 W. This will be for W max. So doing that calculation, we could figure out that W max equals 164 newtons. Okay? Using that, we can now figure out the mass max. It's 164 over 9.81. So we figure out that the maximum mass that this can hold up is 16.7 kilograms. Now we know that each pack of gum weighs approximately 40.5 grams per pack. So we're gonna just go 16, go 16,700 grams over 40.5 grams equals 412 packs of gum. All right, everybody, I just wanted to say thank you for joining us today. That right there is the beauty of math and physics. We could figure out exactly how many packs of gum our funny little table can hold up. Not that we need it to know, but we could find out through physics and statics. Thank you.